Let's have a look at the functionality of the SAMI-Display tool. When you start a program, this is the window that you will see. The SAMI-Display tool gives you the aircraft performance data for several critical functions in the trajectory prediction. Rate of climb at constant CAS, rate of climb at constant Mach, rate of descent at constant CAS, rate of descent at constant Mach, acceleration in horizontal flight, deceleration in level flight, fuel flow in level conditions, fuel flow in climb conditions, fuel flow in idle conditions, and the specific fuel consumption in cruise. The length of the takeoff run, the length of the landing run, and the deceleration on the glide slope. There are two data windows. One, this window indicates the operational flight envelope and the actual performance information you'll find here. In this case, you see that on the horizontal axis the speed is indicated as in CAS values here and here. We are looking now at the rate of climb at constant CAS, and this is the power selection is then max climb power, and the unit on the vertical axis is the vertical speed in feet per minute. On this side, on the left side, you have a window where you have the aircraft type for which we are looking at it and the aircraft state. And here we have a window where you can set the environmental conditions. In this case, the differential temperature profile with respect to the international standard atmosphere. At the very bottom, at the very right, you have a glide slope definition that is only used for the parameter where we look at the deceleration capabilities of the aircraft on the glide slope. Here, for instance, you can set the glide slope to 3 degrees or any other degree, and you see what you can achieve in that case. Now let's select an aircraft to get some practical data. You can select the aircraft type and the aircraft performance model that you want to investigate. Let's look at the game model. We select the game model database and we take the A321. Select the ACP and the AOP files. Now we have all typical information of the Airbus A321. Minimum mass is 47 tons, maximum mass 83 tons. The default situation for which the rate of climb at constant CAS information is displayed is in clean configuration. The actual numerical value will be displayed here, and the draw style, the stylight of the line for which the information is displayed is solid. There are different styles possible because we can display two aircraft types or two aircraft performance models at the same time. So we have a speed indicator here where at this moment and an altitude indicator. So let's say 20,000 feet. At 20,000 feet, when we look at the various speeds within the operational flight envelope, you can read here what the rate of climb in feet per minute is at a international standard atmosphere. In case that we have maximum climb power and the aircraft is maintaining a constant calibrated airspeed. Calibrated airspeed can be read off here. 270 knots, for instance. Then you have a rate of climb of 1,559 feet per minute. Let's have a look at the operational flight envelope display. The legend is here. This is the absolute. So let's lower. The red line gives the absolute flight envelope in function of stall speed, certified ceiling and certified maximum speed. And the normal envelope which is the standard safety margin above the stall speed. That's the green line. So typically you will see the aircraft performance information for the operational for at this altitude of 20,000 feet for the operational speed range. If I change the altitude, then you see that the operational speed range gets smaller. Here we are typically in an area where the aircraft would fly constant Mach, and now you get the rate of climb for constant Mach. You can change the weight of the aircraft, the instantaneous weight, and when the weight changes, you see that the operational flight envelope changes. Of course, not on the maximum speed side, but due to a decreased stall speed. You can select a flight conditions with air conditioning on or off, and the anti-ice on or off, or takeoff power on or off. And for the rest, you can look at all these parameters. If you want to compare two aircraft performance models, you have to look at the standard situation. So let's go and select the aircraft model BADA 3.5. The A321. And you see now that the data is for the BADA model is now in a dotted line, and in the for the game model it is in the solid line. See that there are differences in the operational speed envelope between the two models, and that of course has quite an impact if you are working in a trajectory management environment. The BADA model has, for instance, a lower ceiling than the game model. Let's have a look, see how these things vary. And you see that as function of weight, the game model adapts the operational flight envelope, but the BADA model does not. Very critical. The actual performance data you cannot compare because you have to compare the same mass. Like say if I have 56,000 kilograms, then I should also put 56,000 kilograms for the BADA model as well. And you see that the performance is well, very much the same. Well, start playing with it and enjoy.